You know, in the world of extreme engineering, you've got your regular materials, and then you've got your legends. Materials that are so incredibly tough, so resistant to pretty much everything, that they seem almost alien. Well, today, we're opening the case file on one of those legends. We're going to go deep into a high-stakes technological investigation to see if we can finally crack its code.
And this is really the central puzzle, isn't it? The big paradox that drives this whole thing. When a material's entire reason for being is to defy force, to just shrug off incredible heat and pressure, how in the world do you actually bend it to your will? Let's find out. Okay, so first things first. We need to know our target. The asset at the heart of this entire investigation is a material of unbelievable value. A true superalloy that is, let's be honest, notoriously difficult to control. Its name? Inconel 718. You're going to find this stuff in the heart of jet engines, on the skin of rockets, inside nuclear reactors, basically any place where failure is just not an option. It's a nickel-chromium superalloy, and it's designed to hold its strength in places that would turn most other metals into soup. It really is a masterpiece of material science. But, and there's always a but, here's the catch. To shape something this tough, you usually need these massive, custom-made steel dies and gigantic presses. Now, if you're making thousands of parts, you can spread that cost out. But what if you just need a prototype, or a few custom pieces? Suddenly, the cost is just astronomical. It makes this incredible material totally inaccessible for a ton of cutting-edge projects. So, with the old-school methods being way too expensive, our investigators needed a totally new approach, a really unconventional tool to get past the material's defenses and, persuade it to cooperate, but without using the brute force of a giant die. And that method is called Single Point Incremental Forming, or SPI for short. So forget about that massive punch-and-die setup. SPI is way more like surgical precision. It uses this simple, rounded tool, kind of like a pen, that's guided by a computer. And this tool just methodically pushes and nudges the metal sheet, little by little, coaxing it into its final shape. It's agile, it's super precise, and best of all, it's completely dialless. The whole operation is run by a computer. You start with a design and CAD software, then you generate the path for the tool using CAM software. And then you just feed that program into a standard CNC machine, almost like giving it a set of instructions. The machine then does its thing with robotic precision, just carefully tracing that path and shaping the metal. All right, so with the method chosen, the real work could finally begin. And this wasn't just a matter of trying it once and seeing what happens. Oh no, this was a systematic 9-test interrogation, a whole series of controlled experiments designed to find the material's breaking point and, even more importantly, its sweet spot. So, the investigators basically had 3 main levers they could pull to apply pressure. First, how fast the tool spins. Second, the incremental depth, so how deep the tool pushes with each little pass. And third, the feed rate, how fast the tool moves across the surface. These were their interrogation tools. And this is how they organized the whole investigation. Now, this looks a little complex, but a Taguchi L9 orthogonal array is just a really, really efficient way to test things. It's a grid of 9 unique tests, each with a different mix of speed, depth, and feed rate. This systematic approach means they can cover all the possibilities and find the best combination with, frankly, ruthless efficiency. And after applying all this systematic pressure, the asset, our Inconel 718, it started to talk. The data from these 9 trials began to reveal its secrets, pointing to a very specific set of conditions where it wouldn't just give in, but would perform absolutely beautifully. The first part of the confession was about precision. Get this. In trial 4, they achieved a wall angle of 39.73 degrees. The target they were aiming for was 40 degrees. That is a deviation of just 0.27 degrees. That's an incredible level of accuracy. Okay, the second piece was all about integrity. The original sheet of metal was 0.7 millimeters thick. After being formed, the best result they got maintained a thickness of 0.69 millimeters. That's a deviation of only 1/100th of a millimeter. The material really held its ground. And the third piece of this puzzle was quality. That very same trial produced a surface roughness of just 0.80 micrometers. That was the smoothest, most polished finish they recorded across all 9 tests. So the material wasn't just formed, it was actually refined. So here it is.
the crucial takeaway. Trial number 4 revealed the optimal code: a spindle speed of 300 RPM, a feed rate of 2,000 millimeters per minute, and a step size of 0.2 millimeters. This wasn't a guess. This was the specific combination that unlocked Inconel's potential using this new method.
But, just unlocking the code isn't the end of the story. A true investigator wants to know the absolute limits. So, with the best settings in hand, they decided to up the stakes and run the material through a gauntlet to see just how far it could be pushed before it finally gave up. They started subjecting the Inconel to 4 increasingly complex shapes. We're not talking simple cones anymore. Now they were trying to form circular, elliptical, parabolic, and even exponential curves. Each one of these was designed to push the material closer and closer to its breaking point. So this next phase of testing, it wasn't just about successfully making a shape. It was about finding that exact moment of failure. It was about mapping the boundary between success and, well, a catastrophic fracture. Where exactly does this unformable material finally break? The researchers used a concept they call the forming limit curve. The easiest way to think of it is as a line on a graph. Any combination of stretching and strain that falls below that line, you're safe. But anything that crosses it, well, that represents failure. It's a clear, defined boundary. And right here, we see that boundary being crossed. The material did eventually crack under the incredible strain, but what's really fascinating is that the most complex shape, the exponential curve, actually held on the longest before it failed. So, in its final moments, the asset revealed one last secret: its absolute breaking point. Okay, so the confession is recorded, the limits have been found, the case is almost closed. But we need one last piece of evidence. We need to look deep inside the material itself to see what really happened on a microscopic level. We need the material's fingerprint. This timeline kind of shows the journey of the material's internal structure. We can see it in its raw state, then after a heat treatment, which makes the grains all uniform, and finally, after the SPIF process has done its work. And here it is. This is the smoking gun. On the left, you see that neat, uniform grain structure after heat treatment. But on the right, after forming, it's a complete transformation. The grains are heavily stretched out, they're refined. The SPIF process didn't just bend the metal, it fundamentally re-engineered its internal architecture. This is the irrefutable, microscopic proof of the forces that were at play.
So, this whole investigation did way more than just find a new way to shape a tough alloy. It basically created a key that unlocks all kinds of new possibilities for prototyping and custom parts, especially in aerospace. The case might be closed, but it leaves us with one last, really provocative question. If we can now form the unformable, what impossible machines are we going to build next?